Okay, hello everyone. Mr. Eisinger here. Well, not here actually. I'm at a training session today, so I thought I'd put together a video to show you how to apply mechanical energy conservation to physics problems. It really is as simple as balancing a checkbook, which I don't really know if you guys do any balancing of checkbooks, but it really is not too bad. I want to show you a quick example of how you might apply this kind of math to something that's not physics related. So let's say you have $100 in your pocket. You have 3 friends that you're going to take to the movies, so you and 3 people. You're going to buy their tickets, and so the tickets cost $9 each. You're also going to buy their popcorn, and the popcorn costs $6 each. And you're going to buy their fountain drinks, and they cost $3 each. So the way that you would apply conservation of mechanical energy to physics problems is it's really like balancing a checkbook. You're going to buy 4 tickets. You are going to buy their drinks as well, and so you're going to buy, let's say, 4 drinks. And just to make this a little bit trickier, let's say that you start with $100, and once you buy the tickets, and you buy the fountain drinks, and you buy the popcorn, you don't know how many boxes of popcorn or buckets of popcorn you're going to buy, you leave the movie theater with $40. And the question is how many buckets of popcorn did you purchase? And it really is that simple, and I bet you can do this kind of problem without even writing a lot down. The idea behind mechanical energy conservation is what you start with is what you end with. If you buy 4 of the movie tickets, that's 4 times $9. Plus you don't know how many buckets of popcorn you're going to buy, but they cost $6 each. And you end up buying 4 drinks. Those are $3 each. Plus you still have $40 in your pocket when you leave. All you really have to do now is figure out how many buckets of popcorn you've purchased. And so if you can do this kind of math, then you can certainly do the kind of math that you would need to apply to mechanical energy conservation problems. So you would move things around, solve this, and you're going to see that you would actually buy 2 buckets of popcorn. And it really is that simple. So let's go ahead and look at a few examples of applying mechanical energy to actual physics problems. So the general statement for mechanical energy conservation is up here. MEI is equal to MEF. That's just saying that the mechanical energy is in the beginning is equal to the mechanical energy in the final state. We do have to have only forces such as gravity acting, maybe elastic forces acting. We can't have friction, we can't have air resistance, as we talked before. And so this is the general technique that you would use to solve these kinds of problems. First, you're going to choose the initial and final states. So the initial final state, you need to determine what state you want to start your analysis at, and then what is the final state where you want to end your analysis. Determine which forms of energy is or are present at the initial and final states. So you're going to have to know the different kinds of energy and whether or not they may be present. You would write the equations that would quantify each form of energy present at each of the states, and then finally you would solve. So I'm going to go through this first example with a roller coaster. 1,250 kilogram roller coaster rolls over a hill. That's at point A. They have a speed of 11 meters per second. How fast is it traveling at B? How fast is it traveling at C? We're going to assume that friction is negligible. And also, we're going to answer the question of whether or not the answer depends on the mass of the coaster. So again, same idea, or the principle that I would apply here, conservation of mechanical energy. I'm going to take the initial position to be at A. So MEI is equal to MEF is the way that I would start this. I'm going to say that the mechanical energy at position A is going to be equal to the mechanical energy at position B. Since mechanical energy is conserved, I'm going to choose those as my initial and final positions. The mechanical energy at A, well, I see if I choose this as my reference, and it would make sense to choose the bottom portion of this hill as my reference, that's my H is equal to 0 spot, then I know that up at position A, The object has both gravitational potential energy, and since the car is also moving, it's got some initial velocity, 11 meters per second. I know it also has kinetic energy. There is no elastic potential energy associated with this problem, so we won't include that as mechanical energy. And then at the bottom, once we go through this hill, or go down this hill, we see that the only form of energy they have at this point is kinetic energy. They have no more gravitational potential energy since they're at my reference position, so I would just set that equal to kinetic energy final. And again, that's part 2 and 3 of the problem-solving strategy up top. So I've determined what forms of energy are present, and I've written the equations. Let's go ahead and finish that up by writing what those equations are. mgh initial plus 1/2 mv initial squared will end up equaling 1/2 mv final squared. So now I've written the equations that quantify those. We can see right now, as is often the case, we do see that the mass of the car does reduce out in this particular problem, and we've seen that happen quite a few times. I'm looking for the final velocity, so that final velocity is right over here. I'm going to multiply both sides by 2, so 2g h initial plus v initial squared is equal to v final squared, and then of course I'm just going to take the square root. And I see that v final, the velocity at the bottom of that hill, is just the square root of 2 times 9.8 times 25 meters. It looks like that was the change in height that was experienced during that fall. Plus they started at 11 meters per second, so that's going to be squared. And when I go ahead and check that, let me do that quick calculation. What I see is that they're traveling at about 24.7 meters per second, give or take. And with significant figures, we're looking at 25 meters per second. And again, the value of doing this is that I can determine the speed at the bottom of that hill without really knowing what's going on during this process. The slope of this hill is constantly changing, which means you have a variable acceleration. You cannot use the Fab 4 equations that we've developed in the first semester. You can't use those. Those are valid only if the acceleration is constant. And so we can figure out that speed by ignoring a lot of those details that we would have had to deal with in the first semester. Now we can just use energy and we get to the answer fairly quickly. Okay, so that's part A. If I want to determine the speed at C, I'm going to go ahead and do this a little bit simpler than what we did on this one. So I'll show you how I'm going to approach that method, or approach that problem. I'm just going to choose a different final position. Instead of me going through and saying that I start at A and end at B and then start at B and end at C, I'm just going to go ahead and start this just like I did before with taking the mechanical energy at A equal to the mechanical energy at C, and I'm going to go ahead and just skip right over that intermediate state now of B. And what I see now, the other thing that I'm going to do is I'm going to choose my reference to be right here. So I'm just going to choose a different reference position. Now when I go through that analysis, what I'm going to find out is that I have the exact same kind of energy. I have GPE initial plus KE final, or I'm sorry, scratch that, plus KE initial. And that's going to go to KE final. They don't have any gravitational potential energy at this position simply because I changed my reference position. Now when I go through and solve for that final velocity, it's going to end up being the exact same setup that I had up top. So I'm going to go ahead and try that one more time, except now it's going to be 2 times 9.8 times the change in height now is only a change of, looks like about 10 meters. So now my delta H is only 10 meters instead of 25. They still started at 11 meters per second up top, and so I can go ahead and finish up that problem just like I did the other one. And what I see is that speed is about 17.8 meters per second. So give or take maybe 18 meters per second with significant figures. Again, solving this kind of problem using conservation of energy gets to the answer pretty quickly. There is, I do want to emphasize that sometimes we can make the problem a lot easier by carefully considering where I want to call my, my reference position. Let's take a look at another problem. Ripcord ride at Michigan's Adventure. It's pretty fun if you've never tried it. It's fun, but also a little bit scary. The cable is 90 meters long. Riders are pulled upward until the cable makes an angle of 70 degrees with the vertical. 2 riders of a total mass 175 kilograms are released. And how fast are they moving at the bottom of the swing? Assume no air resistance. So again, that allows us to use conservation of mechanical energy to solve this kind of problem. I'm going to draw a little sketch here, and this is going to involve a little bit of trigonometry. So let's get out those that SOHCAHTOA toolkit, if you will. So here I am. Way down here, we've got, let's just go ahead and draw this like so. We've got 2 or 3 people that are hanging on that ripcord. It gets pulled up, and it does get pulled up quite a bit. About 70 degrees from the vertical is right, and so they're just is about right. They're just dangling there, waiting to pull the cord before they start their descent downward. And so, just like we've had before, it's usually best to complete drawing something along these lines. If that's 70 degrees rather, that would be 20 degrees. And what we're going to do is we're going to release that portion or person here, and as they fall down through this way, they're going to end up converting their gravitational potential energy into kinetic energy. And of course, what we're looking for down here is just how fast are they traveling here. So what is their velocity at the bottom? So let's go ahead and try this from a trig standpoint. Or first, let's do mechanical energy initial is equal to ME final, just like we did before. I'm going to certainly choose this as my initial state. And this is going to be my final state down here. So now I just need to determine what my forms of energy are at the beginning and at the end of my motion. ME initial is just going to be gravitational potential energy initial. Since they're not moving, the only form of energy that they have is GPE, and I should make sure I state what my reference position is. H is equal to 0 down at the bottom, which makes sense. Over here, mechanical energy final is just going to be the kinetic energy that they have at the bottom. I see that we have mgh initial is the only form of energy they have at the top, and that's going to end up going to 1/2 mv final squared. Again, I see, like I saw in the last problem, that the mass reduces out. And since I'm looking for the velocity at the bottom, I'm just going to go ahead and complete that by solving for v final. And I see that v final is equal to the square root of 2gh initial. Again, it doesn't matter how they go through this motion. If they end up swinging along the swing, they would actually have the exact same speed at this point down here as if they had just dropped straight down. Of course, dropping straight down would not be a very fun ride, or at least it would be until you get to the very bottom. Here, we're using that cord to change the direction of my motion, but it doesn't really change the speed of the motion, again, because that tension does no work on that. The only force doing work on this person as they fall is the force of gravity, and it turns out that their speed down here is no different than it would be if they were here. It depends only on the gravitational potential energy that they had, and that is related to the height that they were above that bottom point. Now we still have to figure out what that height is, so this involves a little bit of trig. Like we had before, I'm going to go ahead and determine this portion right here. I'm going to draw a little triangle. That is a 90-degree angle. This is 20 degrees, and I forgot to put down that the cable length was actually 90 meters. So I'm going to use some trigonometry to find this point right there, or that length rather. I see that's the opposite side to that angle, so I'm going to take 90 times the sine of 20 will get me that length, and then since this represents the height, the actual h initial would just be 90 minus 90 sine 20. So let's go ahead and check that. And what I see here is that that is about 59.2 meters. So that is the height of their drop. If I want to determine now their speed at the bottom, V final would just be equal to the square root of 2 times 9.8 times 59.2. And that is about 34 meters per second, which is about 76 miles per hour. And sure enough, if you've ever been on that ride, you are traveling pretty fast down at the bottom. Okay, so again, another problem in which I can use mechanical energy conservation, but I really cannot use the Fab 4 to be able to find this simply because the acceleration is variable. Okay, I'm going to do one more problem with you. This one involves all three forms of energy. It's quite a bit more involved, so I'll spend a little bit more time going through this, and then whatever time we have remaining at the end of the hour, you can work on some problems on your own. A dart gun uses a spring with a spring constant of 450 newtons per meter. The gun is cocked by compressing the spring 12 centimeters. The gun shoots a dart that has a mass of 35 grams. A couple of questions: how fast does the dart leave the barrel of the gun? And how high will it travel if it's shot at an angle of 65 degrees? And let's ignore the mass of the spring. The reason we have this statement in here is that not only is the dart accelerated, but the spring itself is accelerated, and so we don't end up getting all of the energy that we put into the spring. We don't get all of that out into the dart simply because we're accelerating more than just the dart. So let's ignore that for now. This picture, or this set of pictures, is from the physics classroom, and it shows how mechanical energy starts as most of it is in the form of the spring. So the spring is cocked, and stored energy is located in the position of the spring. It looks like they're giving us a little bit of gravitational potential energy, assuming that the dart is starting above the ground. We're going to set this as our reference, really. So we're going to say that there actually is no gravitational potential energy in the beginning. And of course, we have no kinetic energy until we trigger the gun. Once the gun is triggered, we see that the elastic potential energy was converted mostly into kinetic energy, or all of it actually was being converted into kinetic energy. And then as the projectile rises, we see that the kinetic energy is being transformed into gravitational potential energy at the very top. And then as the dart starts to fall back down, we see that the gravitational potential energy is being converted back into kinetic. So we're going to go ahead and determine, one, how fast does the dart leave? That's related to the kinetic energy. And then part two, how high will it travel? We're looking for the maximum height over here. And the trick is, on this one, is that being that it's shot at an angle, it's still going to have some horizontal velocity up here. Vx is not 0 here. So it's still going to have some horizontal velocity. We're going to have to use a little bit of vector resolution to be able to figure out just how fast it is moving horizontally, because it will still have kinetic energy at the top. Okay, so let's go ahead and try this. For part A, we're going to use the principle of mechanical energy conservation like we did before. The initial state is going to be when the gun is cocked and ready to release that dart. So that's going to be elastic potential energy, is the initial form of energy. The final form of energy is going to end up being the kinetic energy that the dart acquires right after it's fired. I see that since I know how to calculate the elastic potential energy is 1/2 k delta x squared, is going to end up going to the kinetic energy 1/2 m v final squared. I notice now that the mass does not reduce out, and that should make sense. If I'm shooting a heavier or more massive dart, it shouldn't be traveling as fast, but it still has the exact same kinetic energy. A more massive dart would be traveling slower, but when you take the product of 1/2 mv final squared, it's equal to the energy that we put into the system. So again, I'm looking for V final, so let's go ahead and solve for that. I see that the halves reduce out, and the final velocity would just be equal to k delta x squared divided by the mass, and I need to take the square root of that. If I wanted to, I could write it as delta x times the square root of k over m. So if I wanted to write it like that, I could. Let's see. The gun is cocked by 12 centimeters, so I'm going to go ahead and put that in as 0.12 meters is the compression. The square root of, let's see, 450 newtons per meter, so it's a pretty strong spring. And the mass of the gun, or mass of the dart rather, is about 0.035 kilograms. So again, paying attention to the SI units, and that will get me the velocity. Let's check that. And hopefully I put that in correctly here. I'm getting about 13.6 meters per second. Please check that, make sure that I haven't made a mistake there. I'm going to go ahead and include one additional significant figure than what I need. My answer would be 14 meters per second based on the sig figs, but I'm going to use that for part B, so I'm going to keep a little bit greater precision. Okay, now part B is going to involve having to deal with some components. So before I do anything else, I'm going to take that 13.6 meters per second, and I'm going to resolve that into an x and a y component. It's being shot at 65 degrees. That would be 65 degrees from the horizontal. So what I'm going to do is I'm going to determine what the horizontal component is, which would be 13.6 times the cosine of 65. That would be about 5.75 meters per second. And the reason I'm doing that is that would be the kinetic energy, or that would be the speed used to find the kinetic energy at the very top, since it is still moving horizontally at the top. Okay, so let's go ahead and see if we can't finish up part B now. I'm going to pause this for a second and reduce the amount of work that I have on the screen, so it's a little bit easier for me to write this. Okay, so now I have a little bit more space to be able to show the work here. For part B, I'm going to go ahead and say MEI is equal to MEF, just like I had before. I'm going to choose my initial position to be the same thing that I had before. I'm just going to say that that was the elastic potential energy that I had right in the beginning. Instead of using 1/2 mv squared, I can choose to use my my starting position to be anywhere that I like. I'm just going to go ahead and say that that's the elastic potential energy that I had right before the dart was released. Now at the very top, I see that I have gravitational potential energy, so I'm looking actually for the height that the dart travels. But because I'm also, the dart is still moving horizontally, it's going to have kinetic energy. I'm going to put that down as 1/2 mvx squared, where the vx is the velocity, the horizontal velocity that we calculated from before. It's going to retain that. As you hopefully recall, the horizontal velocity stays constant during projectile motion, so it still has some kinetic energy. Now, what I'm looking for here is I'm looking for this height right here. So to solve this, I'm just going to go ahead and rearrange everything to get h by itself. So I'm going to pause this because the video is getting sort of long. You try that yourself, make sure that you can solve that for h, and we'll see if we have the exact same thing. Okay, and that's quite a bit of algebraic manipulation there. Hopefully I haven't made a mistake. I know you'll need to look at that and make sure that you have them in the same place, but for the most part, what I get is about 7.76 or about 7.8 meters up is how high that dart should rise from the point of release. And so this distance here, about 7.8 meters. And hopefully I didn't make any algebraic mistakes or mistakes with the calculator. But anyway, that's how you can apply mechanical energy conservation to at least a few examples. I'm going to go ahead and stop there, and hopefully that was enough to give you a good start on your homework. And I will have the homework posted on the board for you. So good luck, and we will see you tomorrow. Go Bucks.